Hi, can I get started? Okay, very good, thank you. Okay. So, welcome back after what seems like a long break. So we didn't meet last Thursday, and we should find a time to schedule another lecture to make up for it. So I'm thinking, is Wednesday mornings good for people?
If it's tomorrow, then yes. Other Wednesdays.
What's special about tomorrow?
We don't have class.
Oh. What time does this class run?
9 to...
Oh, okay. How about Fridays? Saturday evening. Okay, so let me take a look at your schedules and then come up with a concrete plan. For, I'll let you know on Thursday. Okay, so I know it's going to be difficult to arrange. Yes.
You can just exchange it with 11 couple times.
Yeah, you have a class at 11, so I guess, so that's what I've done in the past when I've had to cancel classes. So, that's a good suggestion, obviously, so we may have to resort to that, but you have class at 10:30, just on Tuesday, so we could just do this a couple of Thursdays. Okay, so let's, keep in mind that we are a lecture behind. Okay, so I don't know if you took a look at the coursework website, where I've just added a little note to every lecture saying these are the topics that you're responsible for from the textbook. And today what we are going to do is study duality theory, which is discussed in section 4.2 of your text. And we are going to do this before we do section 4.1, which is sensitivity analysis. So obviously these two topics are closely related, and it's a matter of taste as to which one we want to discuss first. So over the, today, Thursday, and an additional lecture we'll spend on duality theory, sensitivity analysis, and basically that'll wrap up linear programming. So the concluding lecture will be discussing linear programming methods using matrices, and we'll sort of sum up everything that we've done so far in about a lecture. Okay, so that'll wrap up our discussion of linear programming. So for today, I want to do duality, and there are many ways of motivating this discussion. And one that I particularly like is this notion of finding upper bounds that we touched upon before. So here is a linear programming problem, and the goal is to find upper bounds. So x1, x2, x3 are all non-negative, and we'd like to know what the best possible achievable objective value is. But to get at that, of course, one way to do it would be to actually solve this linear program using the simplex method, which we'll do in a little bit. But another related question is, can you get bounds on upper bounds on the objective value? Okay. And we discussed a few tricks in the early lectures, but let's actually try and do this for this example. So can somebody guarantee some kind of an upper bound? Yes. 12. Why is that?
Well, if you try to increase the next one,
Mm-hmm.
furthest you can increase to 2. Never mind. I'm wrong.
Okay. Let's look at an easier problem. Okay. So can we do lower bounds? How do you find a lower bound to such a linear program? Okay, so 0. Okay. Can we do better?
You mean lower or?
Let's do lower bounds first. Lower bound on the objective value. So to find a lower bound on the objective value, what must you do? Well, let me look at the point x1 equals 1, x2 equals 0, x3 equals 0. Okay. Is that feasible? Yes. So this is feasible, and it has objective value four, right? So this implies z star is at least 4. Is everyone comfortable with that argument? Right? So we have a lower bound of 4. So to improve this lower bound, what must you do?
Increase the variables within the constraint.
Well, basically, to improve this, you need to find a feasible solution with a better value. Okay? So maybe you can see x1 equals 0, x2 equals 0, and x3 equals 3. Okay? So that's feasible, z star, is at least 9. Right? So finding lower bounds while requiring some effort is sort of easy. You just have to figure out some feasible solution that gives you a lower bound. Okay? Now, in contrast, finding upper bounds is a little bit more involved, right? Upper bounds are of the form z star is at most something. Okay? So can somebody come up with an upper bound? 10? Why?
Multiply the second constraint both sides by 3 and add to the first.
Okay, very good. So let me actually do this. Can people see that? Yes? Okay. So here's an idea for upper bound. Take, so two times second constraint plus the first constraint. Okay. So what do I get? I get, so x1 plus 4x2 is at most 1, and I get 2 times 3x1 minus x2 plus x3, I'm sorry, 3 times is at most 9, and when I add, I get 10x1 plus x2 plus 3x3 is at most 10. Okay? And my objective value is 4x1 what happened? Well, I guess we can stop. So.
You giving up the class?
Yeah, I don't know what. So do you know why? What happened?
I'm assuming that there is
So could we go on till 10:50 or so today, so that we can at least finish this one lecture? I know you have a. Yeah. Let me check with these guys. Hello. Hi. I wonder if we can start again. I think I'll probably go on a little extra to 10:45 or so today. Is that okay? Okay. Great. So, okay, so let me just use the board and continue with this example. So we said maximize 4x1 plus x2 plus 3x3, and we had these constraints. And the suggestion was to add, take 1 times the first constraint, and then 3 times the second constraint. So this gave me, and this gave me 9x1 minus 3x2 plus 3x3 is at most 9. And when I add, I get 10x1 plus x2 plus 3x3 is at most 10. Okay. And the reason why this is a lower bound, this is an upper bound for the problem that we started, is that the real objective function, which is 4x1 plus x2 plus 3x3, is at most this quantity, which is at most 10. Okay. So this is true because x1 is non-negative. So because x1 is non-negative, 4x1 is at most 10x1. And this is true because of this, and therefore we have an upper bound of 10. So what this is saying is, if z star is the objective value for your problem, then z star is at most 10. Okay. Now, of course, we actually found a solution with value 9. We said x1 equals 0, x2 equals 0, and x3 equals 3 is feasible and has objective value 9. So this implies z star is at least 9. Okay. So without actually solving the problem, we already know that the objective value lies between 9 and 10. Okay. Any question about this? Now, which is it? So can we, is the real value, is z star, is it 10 or is it 9 or is it somewhere in between? Now we don't know. We have to do a little more work to figure that out. Okay. But a natural question might be, okay, is this the best possible upper bound? Can I do something else and improve this? Well, obviously, if there is a solution with value 10, then this is the best possible upper bound, right? You can't do any better. Okay? But we don't know that, and so one may sort of be motivated by the following question: can I find a better bound? Or, can I use the same idea and somehow improve on this bound? And what is the idea? Well, I take the first constraint and multiply it by some number, and I take the second constraint, I multiply it by some number, and I add, and I want to somehow conclude that what I get is an upper bound on the objective value. Okay? So let's actually do just that. So for instance, let's take this general point of view, and let me use y1 times the first constraint. Okay. And let me use y2 times the second constraint. Okay. So what we've essentially done is that we've taken the guessing game out of the picture. So we said, well, here we said we'll multiply this by 1 and this by 3, but maybe there are better multipliers and we don't know what they are. And the general rule that we have in this course is things that you don't know you call by some variable that you try to find somehow. So we're just taking that step to its logical conclusion, and we said this is what we'd like to do. Okay. Now, in order for these to make sense, what must be true of y1 and y2? Can I take y1 to be 7? Yes. Can I take y1 to be -5? No, because this inequality will reverse, right? So if I use a negative number, then minus of this is going to be bigger than -1 times 1. Okay? So if I want to preserve this, I better have y1, y2 non-negative. Okay? So let's just keep that in mind. Now let's actually add. What do we get when we add? We get x1 times y1 plus 3y2 plus x2 times 4y1 minus y2 plus x3 times y2 is at most y1 plus 3y2. Okay? Everyone agree with that? Now, I want to be able to conclude that my objective value, the original objective function, is smaller than this, right? That's the only way I'll get an upper bound. So we want to conclude, so we want 4x1 plus x2 plus 3x3 is at most x1 times y1 plus 3y2 plus x2 times 4y1 minus y2 plus x3 times y2, right? So this is what we want, and we want this to hold regardless of what x1, x2, x3 are. So no matter what x1, x2, x3 value I pick, I want this inequality to hold. If it does, then I can say y1 plus 3y2 is an upper bound. Okay? Now, if you want this to hold for every possible value of x1, x2, and x3, what must be true? Yes?
The coefficient must be slightly bigger than y. First, y1 plus 3y2 would have to be slightly bigger than 4.
Okay, so for this to be true, very good. So you want, so this implies you want y1 plus 3y2 to be bigger than 4. It could actually equal 4, right? But it cannot be smaller than 4. So similarly, you want 4y1 minus y2 to be bigger than 1. And you want y2 to be greater than or equal to 3. Okay? And remember, we also had y1, y2 non-negative. Okay? So we'd like to find multipliers, meaning values of y1 and y2, that satisfy all of these inequalities and that are non-negative. Okay? And whenever we find such values of y1 and y2, we have an upper bound. Okay? So we could take y1 to be 10, y2 to be 0, and y1 to be 10 and y2 to be 10, and I guess you have something satisfying all of this. Okay? So any y1, y2 value satisfying all of these inequalities will give you an upper bound, which is y1 plus 3y2. So we took y1 to be 1 and y2 to be 3. Okay? So certainly 1 plus 3 times 3 is bigger than 4. 4 times 1 minus 3 is at least 1, and 3 is at least 3, right? So the particular choices of y1 and y2, so we tried y1 equals 1, y2 equals 3. And that obviously satisfies all of this, and it gave us a legitimate upper bound. The natural question is, how do you find the best upper bound? Yes?
Would you minimize y1 plus 3y2?
Very good. So we'd like to minimize y1 plus 3y2. Okay? Why? Because the smaller this value, the stronger your upper bound is. Okay? So we'd like to minimize y1 plus 3y2 subject to all of these constraints. Okay? So we started out by trying to figure out the best multipliers. Okay? And we sort of observed that the problem of finding the best multipliers is actually another linear programming problem. So in other words, if you want to somehow conclude that there is no better solution than this one, then in effect you have to solve some other linear programming problem. Okay. Now remember that I motivated all of this by saying I don't want to solve this using the simplex method. I just want to somehow magically conclude that this is the best possible. Of course, by trial and error you may actually do that, but if you want a systematic way of arriving at the best possible upper bound, you have to solve this linear programming problem. Okay. Yes? I don't know. So that's the point, really, that we don't know what these numbers are. Okay. So we wanted, or here we knew, but in general we don't know. And so we want to find those numbers, and finding those numbers is like solving this linear program. No? You don't look too happy. No. So if I want to find upper bounds using this mechanism by combining constraints, taking weighted combinations of constraints, then here I tried 1 and 3 and I got an upper bound of 10. But if I try y1 and y2, then I would get an upper bound of y1 plus 3y2, provided my y1 and y2 satisfy all of these. Okay. For the y1 and y2 to be to give you a valid upper bound, they have to satisfy all of these constraints. Now, given that they satisfy all of these constraints, what values of y1 and y2 should I pick? I want to pick values that minimize this quantity, because I want my upper bound to be as small as possible. Okay? And so I'm led naturally to this linear programming problem that's associated with the problem that I started with. Okay? So, in effect, we are not saving any effort by doing this exercise. It's just a way of motivating this related linear programming problem. Okay. So this is called the dual linear program. Okay. And this is the primal linear program. Okay. So notice that the primal is a maximization problem, the dual is a minimization problem. The right-hand sides of the primal constraints are the coefficients of the objective function of the dual problem. Okay. And the objective function coefficients of the primal problem become the right-hand sides of the dual problem. Okay. And if you look at the constraint matrix, so you have 1, 4, and 0, you have 3, minus 1, and 1. If you look at the columns here, you have 1, 4, and 0, you have 3, minus 1, and 1. Okay. So there are a lot of syntactic similarities between the primal and the dual, and we're going to write it in a more general form in a moment. Yes.
Under general, can we subtract 3y2 from y1?
Yes. You can certainly subtract 3y2 from y1, but that would be using a negative multiplier, right? And so if you want to do subtraction, then you want your y2 to be negative in turn. So as long as you're able to preserve the sign, the sense of the inequality, and you're able to derive an upper bound, you can do anything you want. So in this particular case, you're not allowed to subtract because you want y2 to be non-negative. Okay, so this is the dual linear program, and it has lots of connections to the linear programming problem that we started with. And we are going to explore some of those connections in today's lecture. Okay? Any questions about this? Okay. So in general, I'm going to have maximize C1x1 plus C2x2 plus Cnxn. Okay. So that is a general form of the primal problem. I maximize a linear objective function subject to these linear inequality constraints and non-negativity restrictions. Okay. So the dual is going to be the following. So you minimize, so the dual is going to be a minimization, and you have a variable associated with every constraint of the primal. Okay, so it's going to be minimize b1y1 plus b2y2 plus bmym. Okay. And your constraints are now going to be defined in terms of columns of the primal. Okay. So I'm going to take the first column and multiply by the corresponding multiplier. So it will be a11y1 plus a21y2 plus am1ym. Okay. And you want this quantity to be at least C1. Okay. Similarly, with a12y1 plus a22y2 and in general you'll have a1n y1 plus a2n y2 plus amn ym is at least Cn. Okay. And your y's have to be non-negative also. Okay. So you will never, if you remember the motivation, you will never go wrong in formulating the dual. Okay? So the motivation is to find the best possible upper bound on the primal problem. So you'd like to, and the goal is to multiply all of these inequalities by numbers, y1 through yn. Okay? So to preserve the sense of these inequalities, you want non-negativity here. Okay? Your bound is going to be b1y1 plus b2y2 and so on, and you want to make that as small as possible, so you minimize this. And for you to be able to infer that you have an upper bound, you want the coefficient of x1 in your aggregated constraint to be at least C1. The coefficient of x2 in your aggregated constraint to be at least C2, and so on. Okay? Those are these constraints. So as you can see, you can take the transpose, the constraint matrix here is the transpose of the constraint matrix here. The right-hand side here is in the objective function, and the objective function here is on the right-hand side. Okay. So of course we can write this in an equivalent maximization form, which is that you're going to use multiply everywhere by -1. Okay. So you can, so this is the same as saying maximize minus B1, Y1, minus B2, Y2. And you have minus A11, Y1, minus A21, Y2, minus AM1, YM is at least negative C1. Okay, so why am I doing this? Okay, so that's the maximization version of this dual problem. Okay, now this looks exactly like the problem we started with, okay, except that the B's and C's are interchanged. The A matrix, you take the transpose and you negate it, and that's it, right? You've called the variables y's instead of x's, and you have m of them instead of n of them. So the point is you can take the dual of this problem. Okay, so this is a linear programming problem, and we can take the dual of this linear programming problem by using, let's say some W1, W2, and so on as multipliers. Okay? So I could use W1, W2 as multipliers, so Wn, and I can just think of this as an LP and compute its dual. And you would end up with exactly this problem. Okay? I'm not going to do that because it's just a tedious exercise, but you can actually check that. Okay? You can almost see it, right? So when I have a maximization problem, to get its dual, I'm going to end up with a minimization problem. So let me actually just write out the objective function. Okay? So the objective function is going to be minimize W1 times negative C1, W2 times negative C2, and so on. Okay? So if I take the dual, let me write it here. So I get minimize minus W1 C1 minus W2 C2 minus Wn Cn. Okay. That will be my objective function. And let me write out, so obviously the W's have to be non-negative. And let me write out the jth constraint. Okay. So I should have something to be at least negative Bj. Okay? So there should be something here which is at least negative Bj. Okay? So I'm just doing this exactly the way I go from here to here, I want to go from here to here. Okay? So whatever the coefficient of Yj is, I want that to be bigger than negative Bj. And what's going to be the coefficient of Yj? Well, it's going to be W1, so minus a J1 W1, okay, minus a J2 W2 minus a Jn Wn is at least negative Bj. Okay. This is exactly how the dual of that problem is going to look like. I've written only one of the constraints. But then if you just make the obvious transformation, minimizing this quantity is the same as maximizing C1W1 plus C2W2 plus Cn Wn. So the W's are all non-negative. And this constraint, if I multiply throughout by -1, I get aj1w1 plus aj2w2 plus ajnwn is at most bj. Okay. Which is exactly the problem we started with the w's as variables instead of x as variables. Right? But what you call the variables doesn't really matter. It's the same problem. Okay. So the dual of the dual problem gives you the primal. Okay. So the point is that there is no single dual problem. So you're given a linear program, you can look at its dual, and if you take the dual of that problem, you get back the original linear program. Okay? So you just have these pairs of problems that say something about each other. Right? Of course, you could have started out with this as your primitive linear program. In other words, this as the primal linear program, and you could have gone through the exercise of computing lower bounds on this linear program, and you would have ended up with this as the dual linear program. Okay? So it doesn't matter which one you call the primal and which one you call the dual. So one of these will be called the primal, the other is the dual. Okay? And they play, just as the y's act as multipliers for these constraints, you can think of the x's as acting as multipliers for these constraints. So there's a lot of symmetry here. Any questions about this? Okay. So far I've only told you how you can compute the dual of a problem that looks like this. Okay? Where you have less than equal to constraints, you have non-negativity restrictions. What if you have equations or greater than equal to constraints? So for instance, let me keep those. Let me get rid of this. Okay. So I can write this in a shorter way in the following way. So I could say C is a vector that stands for this. A is a matrix and B is this vector X, of course, is the vector So I'm actually going to omit these transposes, and I'm going to be careless in writing these. Keep in mind that when you multiply vectors or matrices, you want the, there should be something true about the columns, number of columns of the one occurring before and the number of rows of the other, so you can fix the appropriate, put transposes wherever necessary and so on. So with this notation, the primal problem becomes maximize C times X, AX less than or equal to B, X non-negative. Okay. So obviously, C times X I can't multiply, so I should take C transpose times X, okay? Or C times X transpose. You can figure that out. Likewise, so always we define things as column vectors anyway. So you have an A matrix. AX is at most B, and that means, if you take this is an m by n, and X is an n by 1 vector, right? So you want X to be an n by 1 vector. So I should have defined X to be the column vector. Okay. Similarly, I should have defined C to be the column vector, B to be the column vector. So this is just a shorter way of writing or expressing this. Okay? So if you have a problem in this form, then your dual becomes minimize YB. Okay. YA is at least C, Y non-negative. So again, I've omitted transposes in many places, and you should fill those. So this is the primal dual pair of linear programs. Okay. Now, of course, you could have LPs where there are equations. So for instance, suppose I give you a linear program that doesn't look like this, but looks like the following. Maximize Cx, Ax equals B, X non-negative. Okay. This is the form that we work with when doing the simplex method. So how would you compute the dual of this linear programming problem? Okay. Well, one way is to go back to first principles and have equations here and figure out what must be true of the y's so that you get upper bounds the right way. Okay. So go through this exercise that we just went through. The other possibility is to recognize that just as any LP can be converted to this form, any LP can actually be converted to this form also. Okay. So given any linear programming problem, you can always express it as less than equal to constraints and non-negativity restrictions. Okay. So how would you do this here? Well, if I have maximize C times X, Ax equals B, X non-negative, yes, I could say this is the same as maximize Cx, Ax less than equal to B, Ax greater than equal to B, X non-negative, right? So these two things are equivalent. But this is the same as maximize Cx, Ax less than equal to B, minus A times X less than equal to minus B, X non-negative. Okay. So I have now two sets of constraints. Okay. And when I take the dual, I need some y vector and I need some, let's say, w vector. Okay. So I have multipliers associated with this and with this set of constraints. Okay. And my dual is now going to be, so when I compute the dual, I'll have minimize YB minus WB. Okay? So those of you who can't see, let me write the dual here. So from here, I'm going to write the dual, which is minimize YB minus WB. Okay. So that comes from y times the right-hand side, w times the right-hand side. So it's YB plus w times negative b, which is exactly this. Okay. And you have A so y times A minus w times A is at least C. Okay. And y, w non-negative. So these are all vectors. Okay. Y is a vector, w is a vector, and this is the dual problem. Okay. Now one can actually simplify it and observe the following, that this problem does not really depend on y and w individually. It just depends on y minus w, right? So this is the same as y minus w times b. And this is the same as y minus w a is at least c. Okay? And yw being non-negative. Now that is the same as saying I want to minimize, some y hat times b subject to some y hat times a bigger than c and y hat unrestricted. Okay? So let me go through this exercise again to convince you the various steps. So we were given this problem in equality form. We said we can convert anything to a form in which there are only less than equal to constraints. So how did we do that? Well, we replaced ax equals b by two sets of constraints, ax at most b and ax at least b. So the only possibility is for you to satisfy ax equal to b. But this is the same as saying ax at most b and negative a times x being at most negative b. Okay? So you have multipliers for these two sets of constraints, and you apply the syntactic rule. Okay? Just do pattern matching, and you end up with this as the dual problem. Okay? Then you observe that this problem doesn't actually depend on these two multipliers individually. It just depends on the differences between the corresponding coefficients. Okay? So you get minimize y minus w times b subject to y minus w times a bigger than or equal to c, and y and w being non-negative. But observe that if y and w are non-negative, y minus w can assume any value. In fact, this is exactly the trick we used in reverse when converting unrestricted variables to non-negative variables. Right? So here we are coalescing non-negative variables into one unrestricted variable. So therefore you get as your dual problem, minimize some vector y hat times b, that vector y hat is unrestricted, and y hat a has to be at least c. Okay? So this is one way of computing the dual for an arbitrary linear programming problem. Always reduce it to this form, apply these rules, and you get a dual problem. Your textbook explains this. It also tells you, let me tell you the page number. On page 121, it gives you constraints, it gives you relationships between the primal and the dual. So for instance, actually, it's probably just worth writing it down. Okay. So for the max problem, so this is what we call as primal. The min is the dual. So if this is a greater than equal to constraint, then the variable is less than equal to 0. Equality constraint, which means variable is unrestricted. Less than equal to constraint. Okay? So those are the rules for computing the dual. So what does it mean? Well, if in your maximization problem you have a less than equal to constraint, okay? Remember that to every constraint of one problem you attach a variable in the other problem. So if you have a less than equal to constraint in the maximization problem, the corresponding dual multiplier, the dual variable, has to be non-negative. This is the case that we just saw. Okay? This says if you have an equality constraint, then the corresponding dual variable is unrestricted. Okay? This is what I just explained. If you have equality constraints, you get unrestricted variables. Okay? And if you have greater than equal to constraints, then your variables have to be less than equal to 0. Okay? So you'll have non-positive multipliers. All the time, the reason is that the dual problem is a way of getting upper bounds on the objective function of the max problem. Therefore, if you have a constraint that's bigger than equal to, you want to use a negative multiplier so that you make it a less than equal to constraint. Okay? And likewise, variables of this problem create similar rules for constraints of the other problem. Okay? So you have two options. One is to remember these rules, or you really have three options. One is to remember all of these rules. The other is to remember just this nice symmetric form of the primal and dual and reduce everything else to this form. So remember one set of rules. And finally, to remember nothing at all, but to derive everything from first principles, when you will not make any mistake. Maybe a little laborious, but if you keep in mind that the dual problem is a way of getting an upper bound for a max problem, you will never make a mistake. Okay? Any questions about any of this? Okay, so I've also touched upon the matrix notation for linear programs that we'll take up a bit more in the next lecture. Now, in the remaining 15 or so minutes, what I'd like to do is go over a few results about the relationships between the primal and the dual. All of these are explained in section 4.2 of your textbook, but it's worth understanding, so I want to spend some time on it. So I'll pause for any questions that you may have, otherwise we'll continue. Okay. So let me get rid of these. So here is, so for our purposes, the primal will always be the max problem, the dual will always be the min problem, but it doesn't have to be that way. Okay? So keep that in mind when you look at other books. So here is our first result, which is called weak duality. This is obvious by the way we computed the dual. So given any feasible x for the primal problem, and any feasible y for the dual problem. Again, when I say primal and dual, this is really max and min. Okay. Zp of x is at most zd of y. Okay. So Zp of x just means the primal objective value associated with x. Okay? So Z is the objective value that we've been using. Because we have two problems, I subscripted Z with a P or a D, depending on what problem I'm referring to. And what this is saying is, you take any feasible solution to the primal problem, and any feasible solution to the dual problem, then the primal objective value is at most the dual objective value. Okay? This is sort of obvious because this is how we computed the dual in the first place. Okay. So our dual definition was to ensure that this relationship held, because we wanted to sort of say that any feasible solution to the dual problem would give me an upper bound on the objective value. What does it mean for it to be an upper bound? It means that no matter which solution I pick for the primal, the dual feasible solution must have value bigger than that one. So in particular, for the largest possible, for the optimal primal solution, this must be true. Okay. But anyway, we could sort of take as our definition of dual this and try to prove this result. Okay. So you see how these things go. So how do you prove this? Well, let's actually look at the following quantity. Summation aij xj yi summed over all I and summed over all j. Okay. So I'm going to look at this quantity and I'm going to find relationships between, I'm going to relate this to the primal objective value and the dual objective value. Okay? So let's actually examine this the way it's written. Actually, let me put I outside and j inside. Okay? So the way it's written, so this is summation I equals 1 through m, summation j equals 1 through n aij xj times yi. Okay? But because x is feasible for the primal, what is true about this? Okay. So that's just, remember, a21 x1, a22 x2. So this is the second constraint, right? So similarly, when I do this, I'm really looking at the ith constraint. This is just ai1 x1 plus ai2 x2 and so on. So this we know is at most bi yi, right? So this is true because, so here x is primal feasible. Okay? So we have one of the terms that we want. This is exactly, so this is equal to z d of y. Okay? Does everyone understand this chain of inequalities? So I start with this term. I just observe that this is exactly this. Make use of the fact that x is primal feasible. So therefore, this quantity is at most bi, and so I have this. Okay? So remember, not only am I using x is primal feasible, y is non-negative, is also being used here. Okay? Okay, now let's actually look at this in a slightly different way. So one could also rewrite this as summation j equals 1 through n, summation I equals 1 through m, aij yi xj, right? That's just interchanging the summations. You're just adding exactly the same set of terms. But this we have is equal to summation j equals 1 through n aij yi times xj. But because y is dual feasible, this quantity is at least Cj. So this quantity is at least Does everyone agree with this? So here we have used the fact that y is dual feasible and x is non-negative. So if this is at least Cj, then this entire term is at least Cj xj. But this is exactly Zp of x. Okay? So as I read this chain of inequalities, I have Zp of x equals this, which is at most this quantity, which is equal to this, equal to this, equal to this, equal to this, at most this quantity. Okay? So that proves our first result. Any questions about this? Okay, so we know that you take any feasible solution to the primal problem and any feasible solution to the dual problem, this inequality holds. So therefore, this immediately says if you find a feasible solution to the primal and a feasible solution to the dual such that these two quantities are equal, then you have found the optimal primal dual objective values. Okay. So let me state that here. If x is primal feasible and y dual feasible, and if Zp of x is equal to Zd of y, then x is primal optimal and y is dual optimal. Okay. Why does this follow? You just close the gap, right? So suppose, how can x not be optimal? The only way for x to be not optimal is for some other solution to have a larger value. But that solution will, if there is a solution with larger value, that will violate this weak duality property that we just proved. So it couldn't happen. Okay? And likewise for the dual. So here's our first test of optimality, that if we happen to find primal dual solutions with the same objective value, then we know that they are optimal for the respective problems. So this is the sense in which a dual solution y proves that the solution that you found is the best possible. Okay? So you could actually find the right x and then give y as a witness, and anybody can actually check that y satisfies, y is a dual feasible solution with the same objective value as the primal, and be convinced that one cannot do any better. Okay? So this is providing a short proof of optimality of the solution that you computed. Okay? Now, of course, this doesn't say that there is always equality at optimal solutions. All this is saying is, if you're lucky enough to find an x and y that are feasible for these respective problems that happen to have the same objective value, then you know that you're optimal. Okay. Presumably, it's still possible for you to be at a primal optimal solution and a dual optimal solution, and for these two quantities to not be the same. Okay. That possibility is not ruled out by the statement, but in reality that possibility cannot occur also. Okay. And that's called strong duality. Let me just write it here. So strong duality just says if x is primal optimal and y is dual optimal, then Zp of x equals Zd of y. Okay. Okay, so this is sort of like the converse of this, not quite. So this is saying that if optimal solutions exist for your primal and dual problems, then there is no gap. Okay. This says, well, if you find feasible solutions with no gap, then they have to be optimal. Okay, this is sort of easy. This is saying that no matter what LPs you have, as long as they admit optimal solutions, you will always find this to be true. Okay. Let's actually go back and examine this chain of inequalities and understand what must be true for this to hold. Okay. So remember, this is Zp of x, okay, and this is Zd of y. For these two things to be the same, you must have equalities throughout this chain. Okay. So let me write out this chain of equalities over here. So Zp of x is summation Cj xj, okay, and this is at most summation j equals 1 through n. Cj is going to be at most aij yi. Okay. This was equal to summation I equals 1 through m, summation j equals 1 through n, aij xj yi. That's just a different way of rewriting things. And this was at most summation right. So that was the chain of inequalities we had over there. Now suppose you have, so let me just call it x star and y star, just to indicate that they're optimal solutions. Now if you want this and this to be the same, you must have equalities throughout. Okay? Is that clear? So if these two things, so this relationship is true for any feasible x and y. In particular, it is true for the optimal x and y, right? So you want this, 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 this. Okay? Because if x star is optimal and y star is optimal, in particular, they are feasible, and so they should satisfy this chain of inequalities. But if you have equalities here, so if z p of x star equals ZD of Y star. Okay. Now notice I'm not trying to prove this result. I just want to understand when you would have an equality. Okay, what conditions must be true? So if you have equality here, then you have equality throughout this. Okay, so this is actually an equation, and this is actually an equation. Okay. Now, when would these two things be equal? So you must have Cj equal to this, right? I'm sorry? So in other words, this is an inequality, we know that. But when do you have an equality here? When is this inequality an equality? Well, the coefficients have to match, right? Or xj star has to be 0. If xj star is 0, then it really doesn't matter what you multiply it by. But if xj star is positive, then Cj has to be equal to this quantity. Okay. Otherwise, this cannot hold as an equality. It will be a strict inequality. So let me record that. So if this is the case, then either xj star is strictly positive, I'm sorry, either xj star is 0, okay, or Cj equals aij yi star. Okay. So this is saying either some variable, so the jth variable should be 0, or the jth constraint of the dual problem must be satisfied as an equality. Okay. Similarly, for this to be satisfied as an equality, you must have either yi star equal to 0, or bi must equal summation aij xj star. So what this is saying is, so let me interpret it in terms of this primal dual pair of problems, and then we'll stop. So what this is saying is either xj is 0 in an optimal solution, or if xj is non-zero, then the jth constraint here has to be satisfied exactly as an equality. Okay. Similarly, if y2 star is not 0, then it better be the case that this is satisfied as an equality. Okay, so that's what this is saying. But what does it mean for you to satisfy something as an equality? It means the corresponding slack variable or surplus variable has 0 value. Okay? So this is like saying either the jth constraint, so if you look at the second condition here, either yi star is 0, or the jth constraint, the ith constraint is satisfied as an equation, which means the slack associated with the ith constraint is 0. Okay? So these are what are called complementary slackness conditions. So it's called CS conditions. Okay? So what I just argued is that if you have primal and dual feasible solutions that satisfy this, if you have primal and dual feasible solutions that satisfy this, well, we already know by weak duality that they have to be optimal. And we just saw that for them to be optimal, they have to satisfy CS conditions. Okay? Now, similarly, if you take any solutions that satisfy these conditions, okay, you can just look at this chain of inequalities and argue that they will be satisfied as an equation. Right? So give me any two feasible solutions that satisfy these conditions, then the same argument shows that ZP of the x that you started with will equal ZD of the y that you started with. And therefore, you will have optimality. Okay? So the summary is that there are, we figured out many ways or properties of optimal solutions. Okay? So let me just summarize each of them. So first of all, weak duality is true. Any feasible x, any primal feasible x and dual feasible y, ZP is at most ZD. That means if you found a primal feasible x and a dual feasible y with objective values the same, you have to be optimal. The second set of results is that if you have a primal optimal solution and a dual optimal solution, then their objective values are the same. We have not yet proved it. We'll prove it in the next lecture. So that's the result. Then we said for ZP of x and ZD of y to be the same, this entire chain of inequalities must be satisfied as an equality, and that means that these CS conditions have to be satisfied. Okay? Not only that, whenever CS conditions are satisfied, you have this chain of inequalities collapsing into an equality. Therefore, I can combine this observation with weak duality to argue the following, that you give me any x and y that are feasible for the respective problems and that satisfy these CS conditions, then x has to be primal optimal and y has to be dual optimal. Okay? So this is another way of testing optimality if you're given an x and a y. If they satisfy CS conditions, then ZP and ZD have to be the same, and weak duality says that means you have an optimal solution. Okay? So we've also shown that strong duality and CS conditions are equivalent. Right? If you assume that strong duality holds, we derive the CS conditions. But you could go the other way. Start with any x and y that are feasible for the respective problems that satisfy CS conditions, while strong duality holds. Okay? So you prove one, you get the other. So that's what we've seen. What remains to be done is a proof of strong duality itself. So in the next lecture, we are going to go back to the example that we started with and understand what the primal simplex method does and understand how you can view it as operating on the dual in a certain way, and that will also give us a clue to proving strong duality. So this will be the subject of next lecture on Thursday. So I apologize for the longer lecture. No.